picture, an integrated picture of what was going on in the water column. The initial part of the project started with a joint effort between IVS and CCOM at the University of New Hampshire. And CCOM had done a lot of the initial research in different ways to visualize water column information. As you can see in the graphic, they experimented with a midwater fan to show what was in the time series from the multi-beam. They integrated a bathymetric DTM, backscatter, and demonstrated midwater contacts as points within the scene. Now, the initial requirements that we wanted from a midwater tool, first and foremost, was to unify the different midwater formats. Obviously, every different sonar manufacturer logs data in a different way, so this complicates matters. And for visualization and analysis, we wanted to try to unify all of these different data types. We wanted an application to be simple and fast to access the features and extract those features for visualization and analysis. We wanted to be able to manage and view files in nonlinear time. So, traditionally, like with acquisition systems, you would load a file and you hit play, and you would have to wait to get to the interesting part of your data. And we wanted to be able to skip around within our data and move right to areas of interest. For visualization, we wanted to export different metaphors, and we definitely wanted them to be 4D capable, having the time component as well as the geolocation. And we also wanted to have considerations for real-time use. So how would this product move into a real-time environment to give folks on a vessel better situational awareness of the water column during live acquisition. Now, conversion to a common format, we came up with what's known as the GWC. It's the generic water column format. And a good analogy is that water column is to the GWC what bathymetry was or is to the GSF. And we wanted to support a wide variety of formats, the Raison native S7K format, the EM series sonars from Kongsberg, the .all files, the .wcd files, ODIM ES3, which is an A3B file, all of the Simrad, which is also now Kongsberg, but all of their Fisheries formats, Fisheries sonars, which is the raw format for their calibrated sonars, the ME70, EK60s, EK500, etc., and XTF with its sub-bottom channel or single beam channel. The other thing that was important is we wanted the GWC to allow for subsampling or compression of the time series data. Anyone that's ever worked with midwater data knows that some of the data files can be very large. As an example, Raison 7125, some data files you'll get in excess of 14 megabytes per ping. So you can quickly generate a very large acquisition file. So we wanted to be able to deal with that on the back end and do some subsampling to reduce the footprint of the file for visualization. The other key thing is we wanted to allow for integration of external navigation. During acquisition, some systems are set up such that navigation is recorded to an external file, most notably PAWS-MV and processed PAWS using the PAWS Pack software. Now for the workflow, again, simplicity, simplicity, simplicity. We wanted to make it really easy. So there's 4 steps. You import a sonar file, you convert that sonar file to a GWC format, you identify features of interest, and then you export those to Fledermaus objects. So those 4 simple steps run right through the product. Now importing data, most of the major pipelines within FMMidwater are multi-core aware. So if you have a multi-core system, it'll properly load balance across the multiple cores. All the files are indexed to give us our non-linear time-based access, and it's for all intents and purposes file format independent because we support all the major water column capable sonar formats. Data conversion, you have a very simple wizard that you go through to convert to a GWC format. And I think an important note is that another key factor of the GWC is that it contains what we call integrated pings. A lot of the data file formats out there, you have separate packets for navigation. Sometimes a single ping of water column data is broken up into multiple packets due to transmission limitations on the local intranet on a vessel. So you'll get several datagrams that make up your complete swath. And what the GWC has is the packets for a particular ping for the water column are integrated. It contains all the beams, all the time series information, either full resolution or downsampled, and all of the navigation and attitude information that's associated with that ping. Another key feature is that, and I'll demonstrate this later, is that you can concatenate files. So certain topside systems, every so many megabytes, they'll automatically change file names. So you might be transiting a single survey line, but that's made up of 10 or more individual files. Now, you could convert those all individually to GWCs, but it's a little tedious to have to review those individually. So what the concatenation feature allows you to do is it virtually concatenates all the indices and generates a single GWC from multiple files. So you can move through the GWC file as if it was all of the same file, leaving your initial survey files intact. Now, step 3 is the filtering, and we have a number of different ways to do filtering, because when you're wanting to extract features of interest from the water column, the first thing you got to do is eliminate the stuff that's not interesting. Typically, this is low-level noise, beam pattern artifacts, different things like that. So there's a number of different ways that you can do that within the Midwater tool, and I'll demonstrate those later. And those are all basically in this section here. So the first thing we can do is we can limit which beams we're looking at. So we can basically change or reduce the beams of interest. And so now we're focused in on basically beam 75 through about 150, it looks like. The GUI, what we try to do is try to give feedback back to the users so that they understand that there's a desaturation here, so you know that this is no longer an area of interest and not going to be included in any exporting that you do. And you do change the threshold limits just using what we call these are composite sliders. So you can basically drag from either end, or you can drag the center of the slider, and I'll demonstrate that later. You can also set up a particular specific configuration of beams. So if you have bad beams or there's consistent artifacts that you want to eliminate, you can basically select those so that they're permanently off, and you can save that as a custom configuration. The next filter here is through range filtering. A lot of times in the water column you'll get near noise, near transducer noise, bubbles, wake bubbles, that kind of thing. Also at the far range you'll typically get a good side lobe return, and that's another bit that you will want to eliminate for your export. So all of that ends up going away. And the final bit is histogram filtering. That's this control here. So initially you primarily see the histogram of the entire signal. That's the cyan histogram here. And when you change the minimum maximum levels of your threshold, what you're basically doing is you're selecting a portion of the histogram to stretch across the full color range. So it's similar to an image processing technique called contrast stretching. So we're basically selecting a part of the signal level and just stretching that full color range to represent it. And what you can do is you can either clip data, like in this case this is the minimum range and here's the maximum range. You can either clip or clamp the data. So if I clip the data, everything below this level will be eliminated, and the upper level I'm clamping, so I want to keep my high level signal noise. It's just that the color map's going to be stretched across this range here. So now I've reduced what's interesting to just this bit here, and now I'm ready for export. Now, for exporting, working with CCOM, we came up with 4 different visualization metaphors, and these all have different uses that I'll go over. The first is a 4D beam line, a 4D beam fan, a 4D point cloud, and a 3D ISO volume. Now, the beam line is an along track view of one of the beams of the multi-beam system. Of course, if you're using a single beam echo sounder, you'll only have one beam. But in a multi-beam system, you can basically export a curtain that's aligned to the beam angle. So this is very similar, for those of you familiar with Fledermaus, this is very similar to our seismic curtain, with the exception that it's aligned to the beam and it's time aware. One advantage of this visualization metaphor is that there's low distortion across track. Because it's a long track, your resolution is really good top to bottom, 0 to max range, because it's the sample resolution, and your long track resolution is basically your ping resolution. That's different from the next object, which is the beam fan object. So this is a typical swath view, and you're seeing it at the same time with the beam line object. Now, the problem with the swath view, even though it looks really slick, is that you can get high distortion just from the visualization at range. So, your beam, each beam has a specific beam width, and as range increases, how we're displaying the signal level takes up a relatively large area. So that's the distortion that I'm talking about. But it's still a valuable metaphor for viewing your data. The next one is a point cloud object. These are 4D bore site targets. So basically the bore site location of a particular sample in the time series from a specific beam. And that's transformed and geolocated. And it also carries along additional attributes such as the ping, the beam, and the specific amplitude or volume scattering or target strength, whatever you decide to export. And in this case, and I'll show you this live, these are fish traps off the coast of Portsmouth with some mooring lines hanging between the fish traps. These points, of course, are also time aware. The last metaphor is the ISO volume, and this is basically an isosurface object. What we do is we take the filtered data and we ray trace it into a voxel, what I call a voxel brick. So it's, think of a 3-dimensional rectangle that contains voxels of a given size, and you select what the voxel dimensions are, a 1-meter voxel or a 2-meter voxel, and then the data is ray traced into that, and then we build isosurfaces over that data. And this is data that was kindly given us by Jim Gardner and Mashkoor Malik of the 1,400-meter plume that was discovered, I believe it was off the Mendocino Ridge, formerly unknown deep water plume. And this was an early prototype of FMMidwater that was being used to get this data. But this is another interesting metaphor, especially for objects in the water column that have some kind of contiguous volume. And the other interesting thing you can do is, as seen in this picture, is you can nest them and set different ISO levels so you can represent different signal levels to see the internal structure of the object. That's how this was done. And the final bit of the export is straight ASCII. We have a lot of researchers out there that use MATLAB or their own custom Perl scripts or other types of algorithms. So what the Midwater tool does is, after you've filtered your data, you can export to a text file. You get a header representing what the columns are, and it's just column space delimited data of what you've exported. You can pretty much do whatever you want with it. Any questions so far, Josh? Are we all set?
We are doing good.
Okay, I'll proceed. So applications, and actually what's interesting is these are growing as we speak, or if folks are starting to use the water column tool to do more things than we initially envisioned. Obviously hard targets, our hydrographic folks are using the Midwater tool to enhance wreck surveys. So for example, when you do a multi-beam survey of a wreck, that wreck could have masts or cables or nets that have been snagged over the wreck that show up really well in water column but don't necessarily show up in the multi-beam solution. So folks are integrating data from the water column with their traditional multi-beam survey to get a better representation of what the wreck looks like on the seabed. Obviously soft targets, which is kind of where we started, fisheries folks, fish schools, different kind of oceanographic processes, and geophysics and geology are plume folks, what I like to call our bubble people, the folks looking at methane hydrate seeps, deep water volcanoes, and recently in the Gulf, the Midwater tool was being used to help track the oil plume and actually helped find some other natural seeps in and around the area of the Deepwater Horizon wellhead. Now, back from the beginning when we were saying, the big picture of what's really going on in the water column, this is an example of what we were talking about. This is a data that provided EM3002 from CNC Technologies. I apologize, it's not filtered bathymetry. I just gridded it really quickly. But as an example from a typical bathymetric survey, this is what you get. This is an area in and around an in-place oil rig. But when you add the water column data, now you're getting a lot more information. If I add a couple more lines, you can also see, there's a school of fish here that I exported as an ISO volume. There's more fish here near surface. And it definitely gives you a more complete picture of what's going on in the water column over just the bathymetry model. This is another example. This is actually from the stacked view of the Midwater tool that you'll see. This is a survey done of the Richard Montgomery by Allison Leach net survey, and you can see the entire vessel here, and then the vessel was thresholded out, so we thresholded out some of the low-level noise. We did a polygonal selection around the points, parts of the wreck that we wanted to export, and the result of which is that. So that's all water column data. That's not a bathymetric solution. And what they did was they went further and they integrated this data with the bathymetric solution and surface LiDAR data that they had that it's ended up being quite amazing. This was done, with a Reson 7125. This is another view. This is data courtesy of Jens Reinhardt. This is EK60 single beam data. These are methane hydrate plumes with some fish in the near surface. And what's interesting is this is a single beam system, but you can still get a good feel for the 3D shape and volume of a sea plume just by how the survey line is driven. They went over this multiple times. We have data from some folks where they'll use a single beam system to basically do a star pattern over a seep, and when you bring that into the 3D environment, you really get a feel for the shape and size of the plume. This was a case study done by Tom Weber at CCOM UNH where he was using a 7125 pointed out the side of a vessel to follow tuna schools. And this is different aspect views of that data, the fan, then the water column. There's the vessel with aerial photography overlaid, and you can see the school right here from the surface. They had a spotter plane. And there's the point cloud of the school as it progresses, as time progressed. There's another look at it from behind. This is rather interesting data. This is a deep sea volcano. It was EM122 data done by NavOceano. And we have the bathymetry with the plume, and really interesting data because they did several passes over it, and you actually can see how the plume from the volcano spirals in the water column. It's really quite fascinating data. So, in conclusion, capability for collecting midwater data is out there. It's part of a lot of sonars that are currently in the market. It's existed in a lot of the single beam systems and fisheries systems for quite some time. Midwater data can obviously enhance your survey, but previously there were limited tools to deal with this data until we worked on the project to build FMMidwater. It's easy to use. We really try to force ourselves to make it easy to use and straightforward, and provide you a streamlined way of getting raw data to output products. And it's currently used with a variety of users that are out there. A lot of our beta testers, thank you if any of you are on the line. We had folks from the survey industry, folks from exploration, fisheries folks, research folks, so folks that pretty much ran the gamut. Okay, so I'll pause now. Josh, if there are any questions before I proceed to the live demo?
We are still good here, Mo. There's no questions, no hands raised, so if you'd like,
okay,
you could continue on.
Okay. All right, so here we have this is the primary GUI of the Midwater tool. We have the map area, the tree view, the primary display, and then our thresholding. So what I'm going to do is I'm going to walk you through a couple of different data sets and show you basically the key flow process of each. So first thing you want to do is add a sonar file. What I'm going to do is I'll do the fish traps first. So this is a .all file. So what the Midwater tool does is it indexes the data. So when you've loaded a file, you can go in and have a look at what the different packet types are. If you ever have an issue where Midwater says, hey, you're missing navigation, or this data doesn't have water column, you can always open up the tree view here and have a look at all the different packets that currently exist in that data file. So I've loaded my file. I have my little map view here. And the next thing I want to do is convert that data. This is the conversion wizard that we saw in the PowerPoint. I can go to the next page. This is where the Midwater tool tries to figure out where the water column packets are coming from and where the navigation is coming from. Because remember, we can occasionally have external navigation, like from POSPAC, or some of the top sides, like the Kongsberg top sides, they'll actually log .all and .wcd files separately, where the WCD file has the water column data and the .all file has the navigation. And this is where we do our downsampling. So we select, do I want 2-to-1, 4-to-1, no downsampling, and do I want to do concatenation? I'll just leave all the defaults right now, and I'll show you. I have a better example to do the concatenation. So when I say finish, it's going to do the conversion. All right, so now we have our water column view. I can move this timeline. Those of you familiar with Fledermaus, this is right out of Fledermaus, the same timeline control. So I can move through my data, see it in a nonlinear manner. There's some of my fish traps right there. When I was talking about the filtering, the beam filtering here, I can move the control to eliminate beams. If you had some outer beams that were always full of garbage, you could move it in. So I could drag from either end. The other thing I can do too is I can grab the middle and move the whole bit side to side. Hopefully that's showing up good for you guys. The other piece is the range filtering that you saw. So I can move my near range. I can pull in my far range to eliminate some of the data. And then I can also do the threshold filtering. Now, I'll show you this with different sample data, but You can look at amplitude data, you can look at power, volume scattering, or target strength. These particularly reserved for calibrated sonars, which I'll show you. But for thresholding, it's very simple. Click and drag, and then we threshold out, the water column noise. Now, what I'm going to do is I'll take this back out. I'm going to show you the other views. Another view we have, so you can look at the data. This is obviously in a long track view. I'm behind the fan. The other way I can do is I can do a beam view. So now what we're seeing is a single beam of the data. This happens to be beam 1. Left to right is a long track, and top to bottom is range, so 0 to maximum range. And as I move the timeline here, what you get is you get this vertical bar, the time correlator, that shows you where you are in the file along the line. And then there's also this square pipper here that shows you where the location of the vessel was along that line. And you can move through, you can basically move through the water column, select a different beam, like beam 95, and see where, see the specifics from that beam. Now this view you can also zoom, so simply just click and drag. When you click and drag, it clicks out this selector, and when you release, now you've zoomed into that particular part of the data. So we're seeing the fish traps from beam 95 of the multi-beam. Zoom out, you just zoom out here. Now also when you're in this mode, you can also pan. So if there are other interesting features in a different part of the file, you could, or a different part of the line, you can pan around when you're zoomed in by just changing the cursor mode here. So these toolbar options have to do with the map view, and these toolbar options have to do with the midwater view. Now if I zoom back out, the most useful view, and when you want to get right to the meat of the data, is what we call a stacked view. This is very similar to the beam view, so you still have a long track left to right, 0 to maximum range, but the difference is this is as if you took all of the beams and collapsed them down, and what you're looking through the water column and you're seeing the maximum signal level of the samples from all the beams.
You guys hear me?
I can hear somebody in the background. So right here, what we can do is we can see that, obviously this is where our fish traps are, so I can zoom in on that. And then I can threshold out the background signal level here. So at this point, now we're ready to export to the 4D environment. So what I'll do is I'll take you through a couple of different exports. While we're here, we'll just export those points as they are. So this is the export panel. Now, one of the things we try to do with the Midwater tool is the majority of the dialogues, the default values are filled in for you. So very seldom do you have to go in and start poking around with changing options, although you can. But typically you can just say OK. So for example, there's a ping range limit because of your zoom. It knows that you're ping 351 to 1038. You're going to be exporting from all beams. This sonar is pitch and roll stabilized. I want to export the time attribute, and I'm doing an auto projection to zone 19 north. There's preferences in the application that you can set it up so that these are overridden. You can leave it in WGS or NAD83, or you have full flexibility in the output coordinate systems. So I'll just say points. And now what I'll do while I'm running that is I'll bring Fledermaus up. And I'll load, actually let me load a surface. So this is the a DTM surface of the survey area from a bunch of different lines. Let's turn that off. And then I'll open the points. So there's my midwater points of the fish traps. Now when I move my timeline, the points grow. This is typical Fledermaus I can change so that they're cube representation. I can color them by height, those types of things. But, there they are within the 4D environment. Now I can bring other assets in with that, so let's go back to the Midwater tool. I'll go back to my fan view, I'll open this up, and let's export the fan. Again, I'm just saying OK to all the defaults. It's nothing really I have to change in that. It's letting me know that, hey, there's 5 pings in the selection that are missing navigation. We are really careful about verifying that the nav is correct, so when it does all the transforms, you don't get a bust in the object that you're exporting. So I'm going to continue and say yes, that's fine. And then I can bring that guy in. Bring the timeline back. And there's my fan. Now the interesting thing about the fan within Fledermaus is it has very similar capabilities as the Midwater tool. I can change the near-far range. I can change the histogram so that more or less data is displayed. So you basically have the same capabilities within Fledermaus that you did in the Midwater tool for this object type. Let's see, let's export a beam line. Let's go back to our single beam view. And this is beam 95, so I'll zoom in on the fish traps from here, and then I will threshold out background noise and just change the range a bit to bring a little more in, and then I'll export that as a beam curtain. Beam 95. Now again, I selected just this part of the beam. If you wanted to, you could export, you could zoom all the way out, have no threshold filtering, and export the entire line as an object. But I focused in on that certain area, so then I'll bring that in. And let me turn some of these off so you can see what that object looks like. So there's the beam line. Actually, let's change this path to be a line. And go back to beams, and I'll show you the edges. And you'll see if I go from above, that object, is slightly tilted because it's slightly off nadir, but it's similar to the vertical curtain, but aligned to the specific beam, in this case beam 95. So if I move the time slider, and it's also time aware. Now, one of the interesting things you can do with a beam line is you can set up a time window so that only the last, say 100 seconds are shown of the data. Or you can set transparency. If you had this in full, like you didn't threshold out any of the signal level, what you could do is you could, set transparency on that line. And that's that object. The last type of object to export is a what we call a volume. This is an ISO volume. Actually, let me go back to the stacked view. Now, these fish traps aren't necessarily best to do this with, but they are still kind of interesting. Let's threshold out our data. Now, the tricky thing about exporting a volume is you have to pretty much take a guess at what the volume voxel size is. Really, it's based on the depth, the water depth that you're working in, the sample resolution of the sonar. In a future release, what we want to do is try to have the system automatically determine what a nominal cell size is. But for this demo, I'll just put in 3 meters as our cell size. We'll see what it gets us. 3 meter volume. And then go back to Fledermaus. Let's bring that in. Okay. Now, with an ISO volume, I'll change coloring to be attribute-based. Now, since we're generating an ISO surface, that isosurface can be generated at any level in the data. And we also provide the ability, if your voxel data is really dense, you can subsample it. So I'm going to change it back. It's not really that dense. I'll go to subsample 1, and I'll change my isosurface level to that. So effectively, that's the type of object that you're going to get. Now, the plume data that you saw, what I did was, with that, is I loaded several of the same objects within Fledermaus and generated isosurfaces at different levels. So these are going to be associated with the energy levels, the signal level, and the data. And you know, I did one at high energy level, one about midway, and one at low energy level to get the most coverage, and then just set transparency, individual transparency on the outer layers to get that view that we saw in the plume. So again, although these fish traps aren't the best use of this, it gives you a good idea of how this the isovolume object works. It's not time-based. It's not time-aware, so this will always be static within the view. All right. Before I proceed to some of the other data, any questions, Josh?
Yeah, we have one question here. It's just is the GWC format an IVS format, or could other applications write to that format?
Other applications can write to it. The intent is it's a public format. We worked on the GWC with CCOM and some of the sonar manufacturer industry partners, and the intent is for it to be public just like GSF. So absolutely other folks can write to that format.
All right,
okay.
Thanks.
Sure.
That's it for questions right now. Unless anyone else has a question, you can ask it, or if you'd like to raise your hand, you can do that as well. But I don't see anything here right now, so you can continue on.
Okay, let me show you some other interesting data. This is data from Hydrate Ridge. This is an EM122 over a deep sea plume, hydrate plume. This is an example of data that comes in two different formats. The WCD is the water column packets, and the .all contains all the navigation. So I'm going to do my conversion. The Midwater tool automatically figures out that, hey, the water column packets are here, the nav is here, so I don't have to worry about it. And for this, I'm going to do no downsampling. And then I just say finish, and it does the conversion. Now this is a good example data set to show you why you need some of the other, why it's useful to have some of the other different views of the data. The stack, besides just the stacked, the stacked is powerful, and you can see typically right away where your object is, and obviously it's right there. There's our plume. But one of the interesting things with this data is that the plume occurs in a very narrow band of beams, so there's a lot of additional noise that I really don't want to have to deal with. So if I move my time control slider so it's right over that plume, and I go back to the fan view, you can see here's the plume right here, and notice that everything out here is really just rubbish. It's it's unneeded and unwanted. So what I can do is narrow my beams in so that those beams are not considered for the stack. Then when I go back to my stack view, I have a much clearer picture of what's there. And then when I zoom into here, there's my plume. Now this is low resolution data. The long track resolution is very low, and the sample resolution is low, but even with that, as you'll see, you can still get a pretty good feel for what this object looks like. Let me move this up. Also, just as a side note, as you move your cursor over this data, I don't know if you've noticed, but down here in the status window, you always know what the range is. So this is beam range, not a corrected depth. You know the amplitude level of the data, and you know what ping number you're on, and as well as the navigation in time. So if I export this as a, let's do stew points. And let's go back into Fledermaus. All right, and I think I have bathymetry. Yes, I do for this area, which makes it even more interesting. All right, let me open that. data, plume points. Take out a little of the vertical exaggeration. So let's change these to cubes and get a little bigger size. So that's our vent on Hydrate Ridge. It gives you a good feel for the, there's actually a couple of different components of this vent. And another interesting thing too is if you let me see if I have that. If I load the imagery from this, let me make sure I have it. Yeah, I do. And then I drape that on the bathymetry. Excuse me. This is the backscatter from that data. You can see that there's, let's turn this guy off. You can see that there's associated high backscatter reflectors right in the area of the plume. And scientists like Jens Reinhardt can explain this much better than I can, but you're basically looking at different types of deposits on the seabed that are very much associated with this vent. So, this is a good example of the fusion of, I have bathymetry, I have backscatter, and now I have the water column to get data to give me a better feel for the structure of the object. All right. Let me press to another. Yeah, we're getting near on time, so let me move to another data set. This is a single beam sonar, but it's just to show you the interesting data that you can still get from single beam. Do conversion. This is a ES60, I believe, and this data is off of. I'm not going to try to pronounce it. It's Svalbard. It's an Arctic archipelago. And now the interesting thing about the ES is it's a calibrated sonar, so I don't have to look at the data just in amplitude. I can move right to looking at it in volume scattering, and you instantly get a better picture of what the data looks like. So these are different views of pretty much the same seep. As you can see from the map view on the left, they drove kind of a circuitous course on top of the vent. They passed over it several times. And then there's also some biologic, some fish reflectors higher up. But this gives you a better example of, the different ways to look at the data besides, just amplitude. I could do the typical threshold analysis of the data here, but since this is a calibrated sonar, if I move right to volume scattering, the Midwater tool has some defaults. Let me just jump to that really quickly. Has some preferences that you can set up such that if you're viewing the data in volume scattering, it automatically sets or target strength, and automatically sets your default range, dB range, -70 to 34, etc. Ranges can be preset and they're saved within the preferences. So the first time you load an object and you view it in that particular modality, it'll use the default from the preference. And after you move to a different modality, you'll see it. Your new changes will be overridden. Let's see. The last example I want to show you is a concatenation, because it's rather important for dealing with large data sets. And this happens to be ME70 data from over School of Fish, I believe. So this is 1, 2, 3. So here's 6 different files. And those files all progress in a continuous line. If I select them, they'll highlight within the map view. You can see the little highlight box here. So these are all your different sections. Now, if you were going to convert these, if you left all the defaults, you'd end up with 6 different GWC files, which is not very useful. So since these are in a continuous line, when you get to the last page, what you can do is you can turn on the concatenation feature, define a line. I'll just call it line 1. And then when it processes the data, it's going to build what I call a super index, and then it's going to virtually link the files and generate a single GWC file. So now as I move through the data, notice there's no, it's as if the data was one continuous line. And since this is a calibrated sonar, I can move right to SV. And there's our school of fish right here. And if I go to the system, you can see it very clearly. Here's the school of fish, and then some other biologics here, along with some in the near transducer range. I can zoom in a bit more and do a bit more shading of the data. But there's our school. So that's about it. Again, we try to be really efficient in the different the different stages that you have to go through. We want to keep it really simple. So load, convert, threshold, and export. All of your GUI controls are right up front. There's a lot of similarity. We pulled controls from Fledermaus, so once you understand one set, you'll understand the other, and gave you different time-based ways to use to view the data through the synchronization of the map view and the different water column displays. And there's a lot of other there's lots of other additional features that are what I like to call in the double-click level. But we have a good tutorial in the documentation, and if the folks that are out there are constantly helping us improve the product. If you're a user and you believe there's some capability that you think would be good to add or that would help out, just let us know. But that's about it. So Josh, any questions?
Yeah, we have one question here. Let's see. Actually, I'm sorry, we don't. I thought they were questions, but they were just thank yous about the presentation.
Okay.
But again, I just want to go back. If you want to change the presenter over to me here now, Mo, I'm just going to go back to our events page. And at the beginning of the webinar, I said to everyone that that the time for tonight our time, but it's actually 10 a.m. AEST for the Asia Pac people. Mo again will be tonight going through this webinar again with those people. So if you know anyone and pass it on, there's still lots of seats available for tonight's presentation. Also, we have some contact information. So like if you're new to Fledermaus and want some more information about FMMidwater, you can see our contact details here, our email address, and the phone number for your region. And if you are under maintenance and have some more questions, you can contact us like support or call the phone number there listed. And if you want to get some more information about the generic water column data file format, we have a page on our website at ivs3d.com/support/GWC. And you can get more information here. There's a PDF format document that will give you more information about that. But for right now, I don't see any other questions. So I think we are good.
Okay.
So again, I'd like to thank everyone for coming in, and I hope to see you all with our next meeting. And I'll just stay around here for a little bit longer just to see if any other questions come in.